Hello everyone, welcome back to my channel Deep Understanding of Research Papers. Today we are going to discuss the paper LipNet End-to-End Sentence Level Lip Reading, written by Yanis M. Assel, Brendan Shillingford, Simon Whitson and Nando DeFrats. So the paper is from Oxford University, and the first three authors are PhD or postdoc students of Nando DeFrats, who is a very well-known person in machine learning and deep learning. So right now he is working with DeepMind. He is publishing very good papers in reinforcement learning. So Nando DeFrats is one of my best professor. So the overview of this talk is going to be like this. First we are going to understand, or we are going to introduce what is lip reading. Then we will understand what is temporal, spatiotemporal, sorry, that is not a spatiotemporal classification, it is spatiotemporal convolutional neural network. Then we will understand what is a gated recurrent unit. Then we will understand what is connectionist temporal classification. Then we will study a little bit about grid corpus, which is the data set used in this paper to show the effectiveness of their algorithm. Then at the end we see some experiments and results. First let's see what is lip reading. So what is lip reading? So lip reading is when you want to understand what the person is speaking when you don't have the audio. For example, just see this here. So I'm sorry, there is some problem with playing.
Proceed as a great poet if I instead take my nose to the baseball games.
Yeah, you just heard. So the person is speaking something, but there's another video where the audio is muted. So you will, for example, if I mute the audio, for example, here, and you will see only the movements of his lips, and you have to understand what this person is speaking. This is a problem people face when people are deaf, they can't hear. So there is no audio data, there is no speech signal to understand what that person is speaking, but there is only a lip movement where you can go and see a lip movement and try to understand what that person is speaking. So why do we need lip reading? So we need lip reading in many cases. One of the example is if a person is deaf, he can't hear, but if a machine is able to see a picture of a person and read his lips and understand what that person is speaking, and in the text form it prints in front of the deaf people, showing what the person in front of him or her is speaking, then it's a great tool to aid the deaf people. Second is, if you are in a restaurant or in a cafeteria where there is lots and lots of noise, and a speech recognition algorithm like Google Voice or Siri is not able to understand what you are speaking, then this is a good use case, because speech recognition mostly fails when there is a lot of background noise. So if the background noise exceeds the speech level, that means the SNR is very high, then there is a problem for speech recognition system to understand what you are speaking. So lip reading can be one of the good use case in that space also. Now we'll see, is it possible to automate, is it possible to build a model which can see only the lip movement and understand what a person is speaking? Is it possible? This is not a very new problem or anything. Even though this paper was published in 2016, this is not a new problem. This problem was existed from back in 1990s also. People started working from that time itself. But those methods are fine, but this method is a very effective method, and it gives much better accuracy compared to any of the previous systems which were published back in before 2016. And one of the key feature of this algorithm is that this works at sentence level, unlike any other algorithm which work at mostly word level or even at phoneme level. So this algorithm is called end-to-end lip reading, But this is not the only paper which did end-to-end lip reading. So in 2016 itself, a lab in Oxford, VG group, where the VG group people, which is a very well-known lab in computer vision. So there, there is a guy, there is Andrew Zerman and one of his student, Junson. So he is working on lip reading a lot. So he has published many papers in lip reading, but at that time, 2016, even they had an end-to-end lip reading system, but their system was working at word level. So their system was taking mouth feature as input, mouth regions as input, sequence of mouth regions as input, and it was predicting what word was spoken after processing that lip region. But it was predicting words by looking at predicting what words being spoken by looking at the lip movements. But this one not only predicts word, it can predict the entire sentence. So the grid corpus, the data is collected sentence level. That means if a person speaks a sentence and his face was recorded, so that is going to be go as input. The mouth region of that person is going to go as input. The network, in a little bit I'll explain how the network is, and the output is going to be the entire sentence. So it can have many words, it can have 2 words, 3 words, or any number of words, depend on the number of words the person speaks. So this architecture takes care of not only capturing spatial information but also the temporal information also. So for example, if somebody speaks something, the lip movement is going to change. The lip goes up and down, and it widens. So all those changes can, if you take a picture of lip, that one picture will have the spatial information. But when you want to read a lip, it not only depends on one frame, it depends on the previous frames and the next frames also. So there, if you want to capture the temporal information, you have to use some mechanism. You have to incorporate some mechanism into your network so that they take care of this spatial and temporal correlation also. So in this network, so they came up with, they constructed the network in this way. They used spatio-temporal convolutional neural network along with max pooling, spatial max pooling, and then later they feed that to a bidirectional GRU units. So GRU is nothing but GRU is similar to LSTM, but it has a little bit modification that I'll explain it later. So it has a convolution block, which is not only spatial convolution, but it also has temporal convolutions also. And the next block is bidirectional GRU units. Bidirectional GRU units is nothing but bidirectional recurrent neural network. It is similar to LSTM, but it has a little bit changes. So I'll come to that. Then it has a linear unit which goes to softmax. Then the last function here is CTC. CTC is very well known to produce this alignments for unaligned data, unaligned pair data. In our case, you can assume the lip movements over the time is one input, one sequence, and the characters the characters another sequence. Now if you want to find out the alignment between these lip movements and the characters, then it's better to use CTC. If you don't use CTC, then it's very difficult to build this end-to-end kind of system. Otherwise you have to go for hybrid kind of system where you produce the alignment first and then train this kind of deep learning models. Now we understand the blocks inside LipNet. The first block is spatio-temporal CNN. First of all, let's understand what is convolutional neural network. So if you are into deep learning or machine learning, you will know what is convolutional neural network. But for the people who are not familiar with convolutional neural network, it is very simple. Let's say you have an image. Let's say this is the image I have, and let's assume we have done training and everything. We have got very good weights of the kernels. So the kernels are like 3x3 or 5x5 filter, which are like edge filter or Gabor filter or the filters which will detect eyes, mouths, etc. So those filters are learned during training. Don't worry about how we learn those filters. You can read up about ImageNet papers to understand that. For now, let's say we have trained a model and we have got a good features, good filters. So that filter I'll take. That filter is a convert filter which is shown in red block here. So that filter is a small filter. It's called kernel, which will be a 5 cross 5 or 3 cross 3. You can vary. You can change that in your code. So that filter goes and sits on top of this image, and it moves slowly one by one. It depends on the stride. If you mention the stress 2, it moves by 2 pixel. If you mention the stress 1, it moves by 1 pixel. And it goes and convolves over this entire image. And when it sits on top of some part of the image which is of 5 cross 5 pixel, and it multiplies all the values with this filter weights and sum all of the values. It is just like putting some block on top of something, and after you multiply all the value, you sum all of them and project that onto this feature space. So this feature matrix is obtained for this filter, right? Now there is not only one filter, there may be many filters in one convolution layer itself. So this feature map is obtained for one filter. Like that you can get many feature map, depends on the number of filters you have in your network. For example, if I have a convolution layer, first layer has 6 filters, I am going to get 6 feature maps of this red color. So you will get all the feature maps which are stacked next to each other for different filters. So that is concept of convolutional neural network. In reality, this is just only one convolution layer. In reality, there will be multiple convolution layers. After each convolution layer, you will be applying max pooling to reduce the dimension of the feature maps. So let you have an image, this image grayscale image of 40 cross 40, and I have a convolution filter of 5 cross 5. So I might have many filters. I will apply all filters, and I get for every filter I get one feature map. I get multiple features map like this, and I pool each of the, I do max pooling on each of the feature map, and I get the reduced dimension of this feature map which goes here. Now I will have filters in the second layer which can be any number of filters. Those filters can convolve on these feature maps and get a new feature maps, right? So that again we do max pooling here, and then goes on and on. So this is the concept of convolutional neural network. It's not the entire picture. This is just convolutions. You will see after if you read any convolutional neural network paper, there will be a linear layer also, which will take all the feature maps and flatten it to a linear vector, then use that to feed that as the input to softmax. So don't worry about that. Just now understand what is convolutional neural network. Now that you understood what is convolutional neural network, let's go and understand what is spatio-temporal convolutional neural network. What you just saw was just spatial convolutional neural network, because it is operating on the spatial information of the image. Now we have spatio-temporal CNN, where we want to take care, or we want to capture the information which is present in temporal sequence. So the information, in the sense that this temporal sequence is correlated. So for example, if somebody says something, or for example, just like in speech, all the data is correlated, right? So even here, the frames, the lip movements are correlated. Now if you want to capture that information, then you have to do something like being spatio-temporal convolution. So before you were doing only spatial convolution, now we will do both temporal convolution and spatial convolution also. For example, if I have a video, let's say I have 2-second video, each the frame rate is 30 frames per second, then I will have 60 frames. Now each frame, let's say it's only 2D, which I mean it does not have RGB channel, it has only grayscale, which is only one channel. Now I have 60 frames think of this 60 frame as one cube where you have width, height and time. So there are 3 dimensions. Now you want to do convolution on this 3 dimension, and then if you do that, then you get new tensor which is again of 3 dimension. For example, if I take this filter and convolve with this, I get a new blue color cube. If I take this filter and convolve with this entire cube, I get new cube. Then I do max pooling on this cube, these cubes, and get new cubes, and again I can perform spatial temporal convolution, again get this kind of things. It goes on and on. So in similar ways, you want to see and understand this in equation. As I said, spatial CNN does not have the time dependencies. It operates on single image. If I have an image which has width W and width W and height H, and if the number of channels are capital C, number of channel I mean RGB channel. If it is color image, you will have 3 channel. If it is grayscale image, you will have only 1 channel. So you are going to sum. So KW is the width of the filter, KH is the width of the the KW into KH is the filter kernel size. So we do convolution on image X, and we move the filter by I prime during convolution. So that's the stride. So and we sum over all C, W and H. But if you go to spatial temporal convolution, we get one more variable called T. That T is the time. So that is a time variable. So that is the difference between the normal CNN, which is a spatial CNN, and spatial temporal CNN. So just keep in mind that spatial temporal CNN operates on the time domain or time dimensions also. Now this one block of LipNet. So the first block, as I said, it's a spatial temporal CNN. Now it has a one more block which is called by GRU. If you had seen, if you go back to the picture here, you will see the second block is by GRU. So by GRU is gated recurrent unit. So this gated recurrent units are similar to LSTMs. So STMs were invented in 1997, but GRUs were invented in 2014 from Isha Benjia's lab, a few couple of PhDs. So this paper is almost similar to LSTM, but it's not exactly similar to LSTM, but it has small modifications. I'll explain what are the small modifications, and I will also explain what are the equations and how GRU works and much more. So if you see GRU, I should have put another picture where there was a difference between LSTM and GRU, but that's okay. Just remember, if you remember, LSTM as input gate, cell state, then forget gate, output gate. But if you observe here, there is no cell or memory. So in LSTM, there is a particular memory CD available, but in gated recurrent unit, that is not present, right? So we have only the reset gate, and we have update gate. We don't even have we have those 2 gate, and HT here represents the hidden state activation, and we have one more variable called H tilde, which is HT bar, which is called candidate activation. Now, so what happens is HT minus 1 is the previous hidden state, right? And ZT is called update gate. So what happens is this cell, this is a cell which will get the HT, which is the current hidden activation, by operating on the previous hidden activation and the candidate hidden activation. So you should know this candidate hidden activation has relationship with XT and HT minus 1, right? So it has some information about the current input and the previous step hidden activation, and to predict or to generate the current hidden activation, we are going to use this previous hidden activation and this HT, which has encoding of the current input and the previous hidden activation. And ZT here is called update gate, which is a vector which has a weight WZ connecting from Z to X, and UZ connecting from previous hidden state to Z. And this is just a vector, and RT is the reset gate, which is almost similar to ZT, which has WR, which is a matrix of weights connecting from xt to rt, and the matrix of ur which is connecting from previous state to rt. So this is a gated recurrent unit which is similar to LSTM, because that also has gates which helps in reducing the which helps in modulating the input so that we predict the correct output at particular times, and it also helps in reducing vanishing and exploding gradient problem. So having understood both components of, before that, so we had by GRU in our network. So this is GRU. Bidirectional GRU is you process the input in forward sequence and you process the input in backward sequence, and you combine those two forward and backward hidden activation into single activation by concatenating the left hidden activation, right hidden activation, or you sum left and right hidden activations and merge as one hidden activation and pre-feed it to the next layer. So that is that remains similar. Most important part is gated recurrent unit, and how do you construct deep by GRU is, it should be easy, similar to how you construct by LST. Now having understood how GRU works and how spatiotemporal recursion works, the next step is constructing the loss function. So you can think you can see there are many loss function. There is categorical loss function, and if you go to autoencoder, there is reconstruction loss function. But our case is sequence transition problem, where we have a sequence of lip movements and we have a sequence of characters, and want to find out how this sequence of lip movements map to this sequence of character. And we can do this if you don't have the alignment beforehand to train any neural network. We can get the alignment during train itself by using connectionist temporal classification. So connectionist temporal classification again is a object function, and it's used in, as I mentioned, it's used in aligning input and output sequences, and it's most of the time it's used in conjunction with recurrent neural network. And again, it was invented by Alex Graves back in 2005 for handwritten character recognition. Now in our case, let's say we have X, which is vector of, or which is a sequence of input lip movements. We have, let's say we have input video which is of 75 frames 3 seconds, each second will have 35 frames per second. So we have 75 frames and we have, let's say, 10 characters, right? Now we want to find out how these 10 or 75 frames get mapped to, or predict what is being spoken just by looking at this the 75 lip movement frames. So as I said, CTC is not that easy. If you want to construct a CTC loss function, you have to have similar input and output lengths. But in our case, in our example, what we have, the input is 75 frames, but out is only 10 characters. So it does not work because the input and output lengths are not similar. To make the input and output similar, we have to apply. We have to introduce some unknown symbols or blank symbols and make the length of the output sequence to be similar to the length of the input sequence. So that is some other algorithm. That is similar. I mean, in CTC, if you introduce blank symbols, let's say you have two blank symbols next to each other, so you remove both of them and keep only one. Or if you have repeating symbols, you take only one symbol out of it. So there is mapping, reversible mapping from reversible mapping. Let's say there is a space where we project our output sequence, let's say characters, sequence of characters into that space where you get multiple sequences for the same input sequence. For example, let's assume we have a sequence Y, I'm going to school. We have to construct a new sequence which has similar length as the input. Then we project this sequence I am going to school into a new space where it has the length 75, and it is not going to be only one sequence. It will be many sequence, n number of sequence depending on the number of permutations and combinations. Now how do you project back those converted or different length, converted sequences back into the original space, which is I am going to school. The mapping has some rules, 3 rules. You apply those rules to that output sequence, whereas I said if you have repeating symbol, you collapse them into single symbol. If you have multiple underscore, you remove them. So all those rules, if you apply them, it comes back to the original space, which is again readable words, readable sentence. So here B capital beta inverse is that space, and Y is one of the instance of that space. U is one of the instance of that space where we project Y, which is, let's say I am going to school, into the space, and it gets multiple alignments. And you let's say you select one alignment out of it, such that the length of U is similar to length of X, right? Now then you want to maximize this probability of Y given X by summing over all the possible alignments, and by summing the probabilities of all possible alignments given the X. Then if you want to minimize the loss function, what do? You take all the sentences, then apply log to this. You have to first decompose this probability of U1, U2, UT given X into class conditionals, and you can assume each class condition, each output at every time steps independent of other outputs. So you get class conditions which are independent of other classes. Then you can think of this P of U1, U2, UT given X as a product of multiple class conditionals. Then you want to there's one sum here and there's one product here, and you have to put one more sum to take care of all the sentences available in your data set. This is the maximization problem, because you want to maximize the probability to find out a proper distribution which maps inputs to output properly. But in your training, you want to minimize the loss, because you have a good grip on training current neural network using stochastic gradient descent. So gradient descent always wants loss function which are convex. So for that you introduce a negative sign, and you also, to make this product as sum, you put a log, because you don't have log, probability value is very, very small. When you multiply very, very small values, you get something which is out of range or something. So those to take care of all those problems, you put a sum instead of product by adding a log, and then instead of maximizing this probability, you minimize this loss function by introducing a negative minus sign. So that is about CTC. So we have all three components right now. We have spatiotemporal convolution, we have bidirectional GRU, and we have CTC loss function. Now what we have to do is, how do we put all these components together, build a new neural network, then preprocess our data, feed the data, find the loss function, backpropagate in the network for some epochs, and find out if it is working or the algorithm is working or not. So to test the algorithm, these 4 people, Narrative Freya's team, took this grid corpus, because this is the only available data set which has, not today but back in 2016, today there is a LipReading, the wild data set which has sentence level lip reading data. But back in 2016 there was this the data set, sentence level data set which was available was grid corpus. So this grid corpus was collected in University of Sheffield by a few researchers, and there were 34 subjects. So the 34 subjects were supposed to speak 1,000 utterances each. So you will get 34 into 1,000 is 34,000 utterances. And what are the sentences? The sentence is not random. The sentence was constructed in specific order. I come to that. So each video is of 3 seconds, and the frame rate that video is 25 frames per second. So every video will have 75 frames, and the video is available with different HD quality, or if you want 600 x 600 MP4 quality, so you can download in any format you want, but the frame rate is 75, and the sentence was spoken in this format. So you have to construct a sentence by using this these four things. So you can consider a sentence which has a command and a color, proposition, letter, digit, verb. I'll give an example in a minute, but just understand the command can be any of these, one of these four words, and color can be any of these four words, proposition can be any of these four words, letter can be A to Z except W, there are 25 characters, and digits can be 0 to 9, and adverb can be these four, right? Now you can construct a sentence, all possible combination of these sentences, but should be in same order, all possible sentences, and give those sentences to the readers. They will speak the audio, they will speak the sentence in front of the camera. We are going to record audio as well as the lip movements. Lip movements is we are going to record the face of the person. Now let's take an example. Let's see some examples of grid corpus. So
E5 now.
So let's listen again.
Set blue with E5 now.
So he is saying set blue with E5 now, and I don't know if people can recognize him or not. He is a great person. He is actually a professor at University of Sheffield, and he is a top researcher in machine learning. His name is Neil Lawrence. He works mostly works in Gaussian processes, and he is a big guy in Gaussian processes. So when I was searching through the data set, I found that okay, the Neil Lawrence is also participated in collecting this data. So I took the video.
Set blue with E5 now.
So he is saying set blue with E5 now. So as I said in the previous slide, we saw. So he said set blue with E is a letter, 5 was one of the digit, and now. So that was a sentence, and there is a let's listen to one more sentence.
Lay white by S0 again.
So she said lay white by S0 again, which is also on sequence. So that was about grid corpus. Now let's go and understand what was the architecture, how many parameters, what was the input data, what was the output data, how many layers of CNN, how many layers of LSTM or GRU, and all those things. So this is the architecture. You can see the lip movements. I mean, let's say lip regions of video are fed as input to the convolutional neural network. So the convolution filters which you saw before are going to operate on these lip regions, and there is a time dimension, and time dimension is 75 frames. Then after you apply 3 layers of convolution, you come to the bidirectional. So after you apply 3 layers of convolution, you apply spatial pooling, which will reduce the dimension of the output of CNNs, and then you feed that as input to BiGRU. So as you can see, this BiGRU takes input from the forward direction and it takes input from the backward direction, and it processes both forward and backward sequence. So you will get 2 sequences now. You have to merge the 2. So when I say 2 sequences, it's like this. Let's say you have a sequence x1, x2, xt, and your LSTM will take x1 and produce one hidden state h1. It takes h2 and h1 and produces hidden state h2. Right? That happens if you have unidirectional LSTM or unidirectional GRU. But in this case, we are coming from backside also, where we are taking xt and producing ht. So that means at time t, we get a forward hidden state and backward hidden state. So we have to combine those hidden state and make as one hidden state to feed that to the next layer. So that we will do in this BiGRU. As you see, GRU was there before. GRU we explained. So BiGRU is just both forward and backward GRUs. Then the output of that, so we have 2 layers of BiGRUs. So the output of BiGRU goes to linear unit, and the linear unit goes to softmax, and the output of softmax is used to calculate the loss function, CTC loss function, and then we back propagate through the network. So that was all there in the architecture. So as I said, the input mode regions is 100 plus 50 dimensional matrix, which is a 2-dimensional matrix. There is no third dimension like RGB or anything. Then that was obtained by finding the face in a video, then applying face landmark detection using DLib library. Then we get this 50 cross 50 dimensional smooth region. Then we apply STCNN, spatial temporal convolution CNN, for the three different layers spatial convolution. And after that we apply max pooling, and the output of max pooling goes to BiGRU. So the BiGRU processes at each step, processes the input from the CNN at each step and produces the activations, and the return activation goes to linear layer and then for softmax. Then the loss is calculated as usual using CSC. Then we train it with then we do back propagation and all those things, and we train it with mini batch SGD. Then how many number of training occurrences are present? So out of 34,000, there is some issue in the recording for speaker number 21, it seems. So there is no data for 21. So there are whatever remaining number of occurrences were present. They took 28,000 of them, approximately 28,000 of them for training, and remaining of them for testing. So after they train everything, this is the result they got. This is very impressive result actually. So the output, you can see there are two objective measures here. There is something called CR and there is something called WR. So CR stands for character error rate, and WR stands for word error rate. So what is character error rate? Character error rate you compute, it is just an equation, you can look online. I forgot to put that equation here. So character error rate is find out, it's like, for example, if you have substitution errors, you might get substitution error, you might get deletion error, and you might get insertion errors. Now you find out how many of those errors are occurring out of the number of characters you have predicted. Then you have the ground truth also along with you for the rest data, and you see how you compare the output sequence and the ground truth sequence. Then you find out this character array. This is just an equation I told you. Then you measure the output, measure the accuracy. If it is very low, that means your system is very accurate. If it is very high, your system is very bad. Similarly, word error rate. So the as you can see, the ground truth you have is in words actually. It's not in character. Character is the output of CTC, but you apply some language modeling on top of the character sequence, you get words, right? So that's what they have done. They have also done in the paper. So if you see the implementation, actually the implementation is available by Brendan Schillingford, who is I think second author of this paper, who works in who is actually doing DPhil in Oxford University. He has released a torch code for this LipNet. So that code, you go and understand the code, there you will get all the language modeling, doing decoding with beam search and all those things. There's a lot of detail actually there. If you see the implementation, you will understand. So the output may be coming as a characters, but you have to apply language model and get the words. So when you get the word, you might get errors in the words also sometimes. So to calculate what are those errors, we use word error rate. Again, word error, if it is small, it's very good. If it is large, then it's very bad. So they did this scene and overlaps speakers also, and you can look at the details in the paper. So they are getting, the LipNet is giving them 6.4% CER, which is like 90 almost 94% accuracy, and it's giving them 11.4% WR. And with overlap speaker, it's really good because the training speakers are there, and testing speakers also is really good. 1.9%, which is almost 98% accuracy, and 4.8% word error rate for word error rate, and it's like 95% accurate. So, and they have compared this. You can see the amazing thing is they have compared the accuracy of these lip reading systems with some of the experts who can read lip. So there are people who are hearing impaired people, average people. They called some people from University of Oxford, and they asked them they gave them this video where there was no audio, and they asked them to predict what they were speaking, and they get around 47% word error rate. They can't humans can't calculate CR rate, so that it's not a good idea to get. It's not possible to get CR for humans. human subject. So the year people are getting 47%, and I don't know why they did. That also does not make sense. Doing overlapped or non-overlapped does not make sense. And based on LSTM, if they use, they get this much, and if they use 2D LSTM, they get this much, and if you use no LM, no LM is, I think, a no language model, they get this much amount of accuracy. So that's all about LipNet, and thank you so much for watching the video. If you are not subscribed, if you like the video, please subscribe to my YouTube channel for some more papers, and thank you. See you soon.